Hi, everybody. Um, Today we're starting kind of the last half of our unit on transcendental functions. So we've already looked at trigonometric functions, sine, cosine, tan, their derivatives and applications. And for the next little while, we'll be looking at exponential functions and their derivatives. But to start, we need to review some prerequisite skills that we might need. So here we go. First, we want to talk about the graphs of exponential functions. So what I have here, I've used a graphing program. In red, I've graphed the specific function 2 to the power of x. In general, any graph that has the equation y equals b to the power of x, where b is greater than 1, will look the exact same. It will have a y-intercept of 0, 1, and it will have an asymptote towards negative infinity, and will increase at a faster and faster rate. And they'll all have that shape. Bigger bases will have steeper increases, but they'll all have that basic shape. What I've also graphed is a dashed line for y equals x, because I've also graphed the inverse of 2 to the power of x. I've graphed the function log base 2 of x. You guys learned in your grade 12 course that exponential functions and logarithmic functions are inverses of each other. In your grade 11 course, you learned that inverses of each other are reflected in the line y equals x. So for example, the point 0, 1 is on 2 to the power of x. And if you flip the x and y value, you get 1, 0, which is on the inverse. The point 2, 4 is on the exponential function 2 to the power of x. That means the point 4, 2 will be on the graph of its inverse, log base 2 of x. Well, let's just quickly talk a little bit more about what that means in terms of logs. So if the point 4, 2 is on this function, that means that 4 is equal to log, almost messed that up. The y value is 2. 2, there we go, that's better. Y value is 2 when x is 4. Log base 2 of 4. That's a funny looking g. What this expression means, log base 2 of 4, it's saying for a base of 2, what exponent do you need to get 4? Well, obviously we know it's 2 squared gives us 4. So that's why we get a y value of 2. On the right-hand grid, I've graphed the exponential function 1/2 to the power of x. And in general, any exponential function where the base is between 0 and 1 is going to have the same shape. It will also have a y-intercept of 0, 1, but it will be decreasing like so and have its asymptote towards positive infinity. And in the same way, I've graphed the inverse of that, the log base 1/2 of x. So a quick crash course review of what your exponential functions look like and what logarithms are. Let's go through some examples. Now, I did not provide like a PDF lesson sheet for today, because all the examples I'm doing right now are directly from the practice you'll be working on. So I'm doing, for a few questions, I'm doing a couple, and then you'll do a couple. So you can just get a piece of lined paper and just follow these examples along with me and create your own note. In these questions, we're going to rewrite these functions using a base of 2, because sometimes that can be a useful skill. So let's do the first one. And there's no way around it. You do need to do questions like these. You do need to have a basic understanding of like simple powers. For example, I can recognize that 8 is a power of 2. It's 2 to the power of 3. So I can rewrite 8 to the power of x. I just rewrite 8 as 2 to the power of 3, which is, that's what it's equal to. And then I use my exponent rules for powers of powers, which is to multiply the exponents together. So 8 to the power of x and 2 to the power of 3x, those are the exact same function. If the equation might look different, however, they are the same. If you graph those in the same grid, it would be the exact same function. So something to keep in mind as we move throughout this unit, and the same happened with trig functions, is that there's many different ways to express the same exponential function. Let's do b. You can try b if you want to as well. You can pause the video and unpause when you're ready, or follow along with me. In the same way, we write 4 as a power of 2. So 4 is 2 squared. And now I can use my power of a power rule, 2 times 2x. That's equivalent to 2 to the power of 4x. Just for fun, I mentioned you can write exponential functions lots of ways. I could break that up in another way. I could write that as 2 to the power of 4 all to the power of x, which is equal to 16 to the power of x. So 16 to the power of x, 2 to the power of 4x, 4 to the power of 2x. Those are all the same function. So once in a while, we might need to rewrite an exponential function in some other base. Let's talk about evaluating logarithms. So I don't know about you guys, but looking at part A is asking 2, base of 2, to what exponent gives you 5? Now, I don't know about you, but I cannot do that with mental math. So you guys learned a rule for evaluating logarithms like these that involved base 10. And it was this: log base A of B is equivalent to, and I won't prove it here, this is something you guys learned in your grade 12 course, the log of B divided by the log of A, which gives us a way to evaluate these on our calculators. So for part A, log base 2 of 5 is equal to log 5 divided by log 2. And your calculator has a logarithm button. And remember, log by itself is assumed that there's a base 10 there. We just don't write the 10. So log 5 divided by log 2 to 3 decimal places is about 2.322. Why don't you guys try the second one? The second one is asking 4 to what power gives you 66. Let's see what we get. Rewrite that as log 66 over log 4, because nobody would be expected to do that mentally. And let's see what we get. Log 66 divided by log 4, slightly over 3, 3.022 approximately, which is not surprising because we know that 4 to the power of 3 is equal to 64. So it should be just a little bit over 3 should give us a result of 66. And we saw it plays out that way, 3.022. So whenever we need to evaluate some complex logs, we've now reviewed that skill. Once in a while, we might have to apply some of our logarithm rules that we learned. I've picked and choose 3 examples from your practice that illustrate each rule that I want to review. So the first rule is that 2 logs added together is equivalent to a single log. Oh, evidently you don't spell that with an O anymore. It's equivalent to a single log where you multiply I'll say 5 times 2. You multiply the arguments together. That's equal to log 10. And actually, we should be able to evaluate that with mental math. Remember, log is always assumed to be base 10. So 10 to what power gives you 10? This is equal to 1. Or you can do that on your calculator just to verify as well. That's your first, it's a multiplicative property with logs, and it works the other way too. If you had the log of 2 things being multiplied, you can break it up into addition, those 2 arguments. You also learned a rule, and it's kind of related to the first one. Log base 224 minus log base 2 of 3. If you are subtracting, we can rewrite this as a single log with a quotient of the 2 arguments. So log base 2 of 24 divided by 3. 24 divided by 3 is 8. And this is another logarithm we should be able to do mentally. This is saying 2 to what power gives us 8? And that answer is 3. Or you can check on your calculator by doing log 8 divided by log 2. Let's look at D. Again, this is the reason these are out of order, is I just lifted these from your practice and use one of the previous laws. So the log of 0.01 to the power of 3. Well, you guys learned a final rule where if you have the argument of the log is a power, there's an exponent on the argument of your log. You can actually bring that down out front as multiplication. This is equivalent to 3 times the logarithm of 0.01, which we should be able to do by hand as well, because this is saying 10 to what power gives you 0.01. This is like 100th. So that would be 10 to the power of -2 gives us negative, or it gives us 0.01, or you can just do it in your calculator. But yeah, it's -2, and we get -6 as a result here. So quick review of your logarithm rules. You might have to pull them out once in a while. Let's carry on. Once we get to maybe some optimization questions, some application questions involving exponential functions, we might have to solve some exponential equations. So I'm going to solve a few with you right now and just share some strategies. One strategy is to use, if you have an exponential equation, is you can try to solve it by finding some common bases. So for example, I can recognize that 3 and the root of 27, I can write those as a, I can write 27 as a power of 3. So let me show you what I mean by that. So I have 3 to the power of 2x minus 5, and I know that 27 is 3 to the power of 3. Now I can take that a step further, because you guys learned in your grade 11 course that you can write radicals in terms of exponents. The square root is equivalent to an exponent of a half. The square root of 3 to the power of 3 is equivalent to, therefore, 3 to the power of 3 over 2. And you can verify that as well. But we should be able to take those, if 27 is a power of 3, we should be able to write root 27 as a power of 3. And then we can, because both sides of this equation are a power with the same base, if this power is equivalent to this power of 3, and they're both base 3, that means the exponents have to be equal as well. And then we can solve this equation using whatever strategy you like. I might multiply everything by 2 and clear the fraction. So 4x minus 10 equals 3. 4x equals 13. And so x equals 13 over 4 solves this equation for me. That's one strategy you guys should have in your toolbox, using common bases. That isn't always possible, but if it makes life easier if you can do it, for sure. Here we have an equation involving logs. So our goal is to get the x by itself. And so one strategy is to use your logarithm rules to see if you can kind of combine things and simplify things and make it easier for you to isolate a variable. So I can recognize here that I'm adding 2 logs, and we reviewed earlier that I can write that equivalently as the log of the product 5 times x, or 5x equals 3. At this point, I can use my knowledge of logarithms and rewrite this in terms of exponentials. We know this is base 10, right? So this is saying 10, whatever 5x is, 10 to the exponent 3 is going to give us that result of 5x. Base of 10 to the exponent 3 is equal to 5x. Just rewriting that in terms as an exponential instead of a logarithm. And this can actually just be evaluated. 10 to the power of 3 is 1,000. And 1,000 divided by 5 is 200. So you can sometimes solve an equation involving logs by using your log rules and isolating the x that way. Let's carry on. So here's an example, another exponential equation where common bases won't work, because 5 and 50 don't share a common, like there's no, like, we know 5 squared is 25, 5 cubed is 125. We can't write 50 in terms of as a base of 5, at least not easily with the whole number or anything. And just be careful, like you cannot just divide both sides by 5 here. That does not work. The 5 is the base of an exponential function. There's no rule saying that you can do that. So what we're going to do here is we're going to use logarithms. And so I'm just going to type in or punch in here. We're going to use logs. We're going to take the log of each side. So the log of 50 equal to the log of 5 to the power of 2x. I did the same to both sides, so I still have equality there. That statement's still valid. But now I can use one of the log rules we talked about earlier. On the right-hand side, I have 2x as an exponent on that power, 5 to the power of 2x inside a log. I can rewrite this as 2x times the log of 5. And now we have log 50 equals 2 times x times log 5. It's now possible to isolate x by dividing by 2 and dividing by log 5. And that can be evaluated on your calculator. I'm going to do it right now as well. You guys should do it. We'll verify we get the same answer. And I'm going to show you guys an equivalent way to think about that problem. It's really the same method. It just, maybe it's shaped opposite. So I got 1.215. Taking an alternate tack for this one, if you want to just get this down as well. So log 50, what I could have done is I could have thought as of 5 to the power of 2x. If I think of that as 5 squared to the power of x, then I can actually just bring down the x and be left over with 5 squared, which is 25. So you also could have done log 50 divided by log 25, and maybe got there a shade quicker, but it gives you the same result, about 1.215. So we do have the skills to solve exponential equations when the bases can't be matched up. We use logarithms. All right. So that should get you well on your way to the practice I've given you guys. So on Brightspace, I have included a PDF of some skills practice for you guys to work on today. And solutions are uploaded there as well. Next day, we'll start looking at what the derivative of exponential functions looks like. So if I have a function y equals b to the power of x, what would that derivative look like? What are some properties of that derivative? It should be fun. So good luck with the practice, guys. Enjoy the rest of your day. We'll see you guys soon.